Welcome to everyone who's watching this, wherever you may be. Welcome to the third of this year's United Classroom Masterclasses. Today focusing on a really important set of topics we have in A-level physics and also for the world, which is the work on electricity that we do in A-level. I'm Dr. Rob Bastin, I'm course leader for United Classroom in Physics. I'm very happy today to welcome Dr. Dan Rogers, who's a research associate at the University of Sheffield, working specifically in the electronic and electrical engineering department there. His work includes working on grid systems of batteries that are going to solve some of the big problems in the world that we see at the moment, but also he works on lots of other things to try and solve the big problems in electrical theory that we kind of try and understand a little bit in physics, but I hope today also we're going to get a little bit more about the applications of that physics and how engineering solutions can actually save a lot of the problems in the world. So without further ado, I'm going to pass over to Dan, who's going to regale us with wonderful things. Now, before we actually do pass over, sorry, that was a cue point. Just to remind you, if you are watching on the YouTube channel, you can click on the link that should pop up, which says join in with this Hangout, and it'll come up with a place where you can ask questions. Alternatively, you can email me, and a link appears in the bottom of the YouTube channel as well, where you can email me questions. The students, obviously, they have the benefit that they can ask questions themselves. So when we get to the point in the session where we have a Q&A at the end, feel free to add in those questions. And just to remind the students, you can mic on if you want to ask a question as we go as well. So feel free to do that. I'm sure Dan will be happy to accept those too. Okay, definitely this time over to Dan. Go away with it. Take.
Hi then. Thanks, Rob. As Rob said, my name's Dan Rogers. I'm a engineer at Sheffield University, a research associate. So what that really means is that I've done a PhD and I've carried on my research there, based in those laboratory systems there. And so I'm researching grid scale battery storage systems. So what I'm going to do is talk about why, the whats and the hows of this, and I think you'll be quite surprised how I use really not much more than A-level physics every day, and pretty not much more above that level. So I'm going to just turn my PowerPoint presentation on. Hopefully this will work. So I'm going to screen share. It should work. And I'll do that. And then if I here, and then I'll do that. So hopefully you can all see that. And basically I'm in charge, or one of the main engineers in charge of the Willenhall energy storage system. So what that is, it's a, for want of a better term, a massive battery just outside the West Midlands, in northwest of Birmingham. And we installed this, we basically commissioned it a couple of months ago. We had our grand opening. So I'm just going to talk about that big battery system and why we need it and how we built it. So getting straight on with it really. So electricity, it's essential to everyday life. I'm sure anybody watching this presentation requires electricity to watch it. And really, as you're well aware, that electricity is just it's a general term for lots of different slightly different physical effects associated with electrical charge. And you utilise these effects every day in appliances, all the time. I mean, I think that's a shot of my kitchen a few nights ago when I was writing this presentation, and it's got, I think I've got about 1, 2, 3, 4, 5, 6, 7 appliances just in that corner of my kitchen worktop. And as a slight twist, if you added them all together, it would actually blow the circuits in my house, but you never ever use them all at the same time. So that's why you won't blow, you'll knock the fuse out. But essentially, all really useful stuff. We need it all, and there's just a standard light. Can't do without your lighting. But the key point is we need all this electricity. How does it get to us, and how's it generated, and how do we make best use of it? So what you've got to get your head around is what's the size of this system we've got in the UK. And we're quite small. I mean, it's nothing compared to the States. Last year, I mean, in 2014, we used 330 terawatt hours of energy. So that's, if you think a car battery is roughly about half a kilowatt hour. So if you wanted to run the UK on car batteries, standard car batteries, you'd need 600 billion of them for the year. Charge them all up at the start of the year and that would run it. It'd be a bit more complicated than that, but it just gives you an idea of scale. And historically, because we've always used fossil fuels in the past, it's much more efficient to generate this stuff at a big grid scale size. And it's the best thing to do is have a massive turbine and a massive coal plant, and then that was the best thing to do because you've got those economies of scale from your you've got more bang for your buck, for want of a better term. But of course, having all these centralised power stations, and you've probably got several dozen, or used to have, of that size in the UK, you've got to transmit it. And then all of a sudden it starts to get a bit complicated because you get losses. And as Rob said, I apply I'm more of an application sort of person because I'm an engineer. I apply science to everyday problems. There's obviously a crossover between science and engineering, but I'm more of the application side. And really, it's just not much more than Ohm's law on this, just to get the idea around the problem, because as you may know, that the losses of any transmission, the power is proportional to the square of the current. So as soon as that current starts going up, the power, you square that, the current goes really fast up as you start increasing. So what you've got to do is you've got to reduce that current as small as possible if you're going to be transmitting electricity for any distances, because that resistance will make those losses increase very quickly. So what you've got to do is you increase the voltage. You get the current low, reduce Ohm's law, you need high voltage to have the same amount of power running through. Or the same amount of energy running through. So that is why we run at 400,000 volts on some of the longer distances in the UK. So the thing is you're moving all the electricity around the grid, all around the UK, but the problem is you're going to be lifting up voltages and down voltages because you're going to be generating at several thousand volts in a power station. You're going to be raising up to hundreds of thousands of volts to get it somewhere, and then you're going to be bringing it down again to a safe level for your house. So, because obviously you can't have 400,000 volts in your house. So there's got to be, and the reason why we use alternating current, AC, is because of this device in this picture here. It's a transformer. That's quite an old one. That's a refurb one from the 70s, actually, an oil-filled one. But essentially all that is a method of raising the voltage and lowering the voltage again. But it's really cheap and really easy. But it relies on you having AC, and that's why we have AC. There was a big argument about 100 years ago, a bit more than 100 years ago now, whether it was DC versus AC. And at the time, there wasn't an easy way of raising DC voltages up and down. It's still not that easy, but there are methods of doing it, and there are some long-range DC links in the UK. I'm pretty sure the cross-channel ones are DC, for example, for other advantages. But for cheap, easy, and historic reasons, we use AC. Now, AC current is generated because of how we generate electricity. So in this instance, you've got a central shaft there, and all you're doing is spinning some kind of magnetic system round. So you've got this magnetic system, and it's spinning round. And so if you're passing a magnetic object round, passing coils of wire, you're going to be generating electricity there, and 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 there. And the reason, and what's happening is because the angle you're changing, that's going to be changing in a sinusoidal manner. So this is going to go up and down in a sinusoidal manner. And that's why you get 3 phases. And the reason why we have 3 of these coils is just a really, it's a way of compacting things. You could have 1 phase, but you're not getting, if you're making a cylindrical machine, you might as well try and get things out, more things around it. In fact, you can get lots more phases on machines. You'd actually probably have an extra core there, an extra core there, an extra core there, and you wind it so you're getting more sort of distance as it passes round. So, but essentially, you've probably heard the term three-phase. And three-phase is what everything more or less is generated in the UK. And in the UK and Europe, it's 50 hertz, and in the States, it's 60 hertz. And there's several particular reasons why we use those frequencies. So, but essentially, that's basically what we've got, and we've had that for more or less 100 years, really. Now, getting in more detail, your frequency of this, say, these three phases moving around, and then as you split off to each individual house, each house often just only has one phase each, but essentially everything's revolving around this 50 hertz, the way you generate it, and a lot of machines and equipment are relying on that 50 hertz. Now, I was going to show you an induction motor I've got at the lab, but we had a bit of an internet problem in the lab, ironically, so I haven't got it, but essentially those motors, and there's thousands of them, probably hundreds of thousands of them in factories all over the country, all over the world, that are dependent on that main frequency because they're kind of made and tuned to run at that speed. And even silly things like that's not, I think that's off my microwave at home, and that's that clock, I'm pretty sure, is frequency dependent. Because what you do is if you've got a 50 hertz frequency, you can count off that time, and you can have quite a basic clock. Because that's why, if you notice on cheaper household appliances, you see the time clock the clock drifts after a few weeks or a month or so. That's because the frequency isn't actually constant. They try, but it's not actually constant. So, in essence, you can kind of get why. So everyone's running at this 50 hertz thing. But as you can imagine, all these mechanical components are tuned to run at that 50 hertz. So if you get a slight deviation of that, all of a sudden you get efficiency losses, and even real quite dangerous problems. If you're running a generator and two generators and they're not syncing into the grid, you've got to sync those generators roughly at 50 hertz, otherwise one generator might be feeding straight back into another one, and all sorts of things are happening. And it isn't just about frequency, it's about the level of voltage, it's all sorts of things. But my area of research, and what I'm doing particularly at the moment, is to do with frequency regulation. So what do they do about it at the moment? Well, what they usually do, actually, when the electricity, there's too little of it, so what happens is if there's a sort of, there's too much load, the frequency actually drops because the generator's struggling really hard. So what they do is they pay big users to turn off, so like steel mills and things like that, they'll actually turn off for set periods. And in times of excess energy, which happens because suddenly a load drops somewhere else, I don't know, they have to shut something down for an emergency, and suddenly the frequency really starts climbing quickly, they'll have to dump energy. And one method they do that is they basically bypass the steam round power station turbine, so power isn't actually used by the turbine, it's just venting straight out of the cooling towers. So you've got all these issues where they're wasting energy when there's too much, and they're still using it when you're still using extra when you need it. So for example, this little diagram, my dodgy little diagram here, you've got your power station, you're venting it when you've got trouble, you put in more standby, so this is a waste because you're just dumping it. And you actually use this could be a generator, it could be a diesel generator, it could be a gas turbine. I spoke to one guy who used to own well, he didn't own it, his company owned it. They had for want of a better term, it was basically a Concorde engine linked to a generator, and they'd get a call, and within seconds they could fire this thing up with an enormous bang, and it would generate electricity in a very short time, incredibly unenvironmentally friendly, but it did top the frequency up. So there's a problem here, really, because what we're doing is if you could somehow keep this bit, save it for later, and then put it back in there, it's like money for nothing, really. So that has kind of been the holy grail not for decades, really. Frequency regulation is not an old thing, particularly using storage. So we got a project. sought funding for a project involving storage of electrical energy on a grid scale, and these are the partners working on it. So it's quite a big project. We work with other people as well, but these are the people I've worked with so far. So you've got, for example, AEB, they make a massive inverter, which I'll talk about in a minute. Western Power Distribution, they run a big chunk of grid in the UK. There's E.ON, who we're working with at the moment. They're helping us, and we're helping them learn more about how to use batteries on the grid. Toshiba, they supply their actually batteries. And then there's Store, they made some of our cabins. And Sterling, they're like a specialist electrical contractor. So even though I do research, actually a lot of my job is about management and stuff, sort of talking to these various people and making things run sort of smoothly. And we were going to try and play a video, so I'm going to just try. You'll have to bear with me while I try and do this smoothly. You can see my screen. Right, that's everyone. Now if I can just go to my right thing. Where is it gone? Where have we gone? I'm in Firefox. I'm in Firefox. Yes, there we go. And this is the video. Hopefully it all works. This is what we built. So what we've done, so that's our battery system, and so what we've done is we've rearranged everything. So what we've done is we've stuck the power. We had this before, but now what we've done is we've almost like joined the line here, really, because now we can store when we've got excess and put back in when we haven't got enough. Now, obviously, people have been doing this for decades, probably as long as they've been generating electricity, they've been storing it in some ways. For example, I don't know whether you know, but this is an electric mountain in Wales, for example, quite a pioneering project of its day. It's an enormous pumped hydro system. So the very fact that we've all got electric kettles really causes a huge spike in demand in the mornings, and at other times. For example, at Christmas, when it's the Christmas special of EastEnders, when people go out and make a cup of tea, really puts enormous strain on the grid. And what you do is you have a big reservoir at the top of the mountain. You pump it up there when you've got too much electricity, and you open the taps when you've got too little. That's not the only way, though. There are many other types. I've just named a few here. CAES, that's compressed air storage. There's a very large system in Germany. There's a big one in the US, and that's been going a long time as well. There's also faster stuff for shorter, high power, low energy systems. So for a lot of power very quickly. Flywheels, Beacon Power in the US, they've been pioneering that. And I went to a very interesting talk the other day at Newcastle University, where they're experimenting and really working with supercapacitors at the moment on a microgrid system they've got there. So there's other methods of storing energy, but they've all got their advantages and disadvantages. You know, pumped hydro, it's extremely expensive to build, and you need a mounting, which is quite tricky, particularly if it's geographically dependent and possibly sensitive. Compressed air storage, you don't need a mounting, but they're lower efficiency. Roughly about 50% is the figure that's often quoted, because you've got to pump it, compress it, and then warm it as it comes back out again, because as it's decompressing, it's very cold, so you have to pre-warm it before it goes into turbines and all those other things. So there's flywheels. They're a very interesting one because they don't actually, they're high power, low energy, and the response is very quick. But getting a large capacity of flywheel systems can be a bit tricky. Very old system though. I mean, if you take away the electrical component, flywheels have been around for thousands of years. There's records going back to prehistory with pottery turntables, and that's essentially an energy store. And then you've got supercapacitors, which I've just spoken about. So why have we chosen batteries? Well, although it's quite a new system in the UK, it's the biggest lithium titanate battery in Europe, I believe. But they're not actually that new idea. I mean, there's been lead-acid battery systems around for a long time. But the problem with lead-acid batteries is, well, there's a big advantage and a big disadvantage. There's a big disadvantage is they do wear out quick. As anyone who's had an old car or parents of an old car, it's often the battery is the weak point. And they don't like low temperatures or very high temperatures. And the cycle life, and when I say cycle life, you mean a charge and a discharge between certain limits, is only in the hundreds, maybe 1,000 with a fancy lead acid with a few funny chemicals in it or introduced to it. So they wear out a bit. Lithium ion, oh yeah, the advantage of lead acid though, and that's being proffered a lot by the Advanced Lead Acid Battery Consortium, I think they're called, but they are very recyclable. You're 98% recyclable, so that's something to consider. But lithium ion, however, is the big. To be honest, it's very it's trendy at the moment because it's used in so many things we use every day, from our laptops to our mobile phones. The other thing is they are much more resistant to cycle life. They're smaller, which not really is a problem with grid scale stuff because you've got a container in the middle of the field, you're not worried about weight or size really. But they are a bit. They're just a bit. They are, but they are much more compact. They are susceptible to temperature variations, though. However, or most of them are. And another thing is considering there's lithium ion and there's lithium ion. There's lots of different types. There's lithium. I always forget. There's lithium ion phosphate. We use titanate. There's loads of others, and they are quite pricey too. So we went for lithium ion titanate. I think is the full name. It's very impressive cycle life. Our ones. The Toshiba believe there's over 7,000 cycles are possible, which is enormous compared to anything lead acid particularly. Some lithium ions, other types of lithium ion perhaps, but titanate really is the big cheese on this sport. However, they're the most expensive by a mile. Our ones cost 1.3 million, that container. They're big, they're not very particularly small or light, they're quite chunky for their size. But they are resistant to temperature change. And the other key thing about lithium, and particularly titanate, they don't mind if you really, for want of a better term, thrash them. You can really hammer them quite hard, and they do quite well. We're only limited by a transformer, actually. The amount of electricity you can get through our transformer. But so we had basically we'd done some consultation with some people, and we kind of had this specification because we knew things were going to change on the national grid. We knew there was going to be new incentives coming out, which companies would be interested in, and the UK would be interested in. So what we decided to do, we decided to research an area which was probably going to happen, and just by a bit of luck, some good judgment, it has happened. And I think that some news came out the other day actually regarding that, but I'll come to that in a minute. So essentially we wanted 2 megawatts, so 2 million watts for 15 minutes, which is about 3,000 homes. And you've got to go to 0 to 0 to 2 megawatts in 2 cycles of the mains. So when I say 2 cycles of the mains, so cycles, AC is 50 hertz, so you've got 1 cycle, 2 cycles, 3 cycles, and 50 hertz is 20 milliseconds. So really 2 cycles, so we've got to go from 0 to hero, from here, up here somewhere, about here somewhere, in 40 milliseconds. And this was a result we got a couple of months ago, and it proved we can do it. It does do it. There's a couple of other issues why it doesn't do it all the time, and that's called research. So, but it does do it. But there's another thing you have to work out when you're building these systems as well, because batteries are a bit weird in general. When you discharge them, when you put a load on them, so when they're no load, but you've got a battery sitting on your desk, it's at a certain voltage. As soon as you put a load on, the voltage output drops. And then when you discharge it, the voltage drops again. So essentially, whenever you're working out current coming out of a battery, you've always got to be careful you're using the lowest possible current. Sorry, the lowest possible voltage you're going to get out of it, because that will mean the highest possible current. So these are some discharge curves of some weird lead acids actually. They're carbon enhanced lead acids. They're a particular thing. And if you notice, these are the carbon enhanced ones. And that's your standard car one, really. That's your standard car battery. So quite a different characteristic. Even on a, so like I was saying, there's different types of lead acid. There are different types of, different types of lithium ion. There are different types of lead acid too. So loads of different stuff going on. But essentially, our minimum voltage across our big battery is about 520 volts. So you're talking near the 4,000 amps at 600 volts. So I think we worked out the other day, it's about this battery will basically boil enough, it has enough energy to make enough water for 50,000 cups of tea in one discharge. So they're big numbers really. And these are the big things. These are Toshiba cells. These are not the total key to the system, but one of the big components. And these are extremely pricey, but very, very good skib cells. I'm not going to go into too much detail, but the key point is to remember is you have cells in a battery. So your lead acid battery has 6 cells, 6 2-volt cells in it in your car, and these have. And when you have a cell, you kind of may restrict it to the physical makeup of the properties, and then you bolt it together. Normally, we'd call it a battery, but Toshiba called it a module because you end up with a big battery. And here's the inside of our big battery. It's there are 880 of those big black modules in there, and they all clip together, and they're arranged in strings. So you have 40 strings as well. So you've got 22 modules in each string, and you've got 40 of them, so 880 of them. So you've got an engineering compromise, basically. You could mount those cells in all sorts of funny ways, but they've chosen to do that because it suits most of their applications. They use them a lot on buses in Japan because they want the fast charge rates. So here we go. Yeah, this is a little bit of a maths, but essentially what you've got to remember is there's 40 strings in parallel, all clonking in and onto. Oh, hang on a minute, I'll go back. So along here, you've got the big central buzz bars, 2 of them. Well, 4 of them actually, 2 along there and 2 along here, positive, negative. And up here are all these switches, and they click, 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 click on each string. So, and then all the strings are online, and then you're off. So you've got a battery, and there's your transformer. That's your big 11 kV transformer. There's your inverter. Now an inverter, what that does, as you saw in the video, it converts your AC to DC, and it's bidirectional, so it can also convert DC into AC, which is it's pretty clever. So what you've got is your AC breaker, and your DC breaker, and then your battery. So what happens is you close this first, you charge up, there's some capacitors on there that you have to charge up first, then that closes, and then it does its stuff, and then that closes, and then your battery's live. So I'm now going to show you a video of us starting that up yesterday, actually. I was down there yesterday. Fingers crossed this will work as well. Yeah, here we go. So hopefully you can see that.
Dan, it's a little hard to hear the noise on there. Perhaps it would be worth voice-overing it.
So what happened there so what we did. I'll just play it again, actually. So what we got. So Alex is helping me out, and what we've got here is this was a trace. We were working out what the actual current was doing, and then here. And then if you get to about so Alex, this is the operating system for turning on the inverter, and then the big bang in the background you'll get in a minute. So what that was there's this top breaker here in the inverter just snapped shut. So what you've got is, these are sprung loaded because the power is so high. What happens is you have a motor here, and it winds it up, and then winds up a spring, and then the spring is released, and then it closes the breaker really fast. And the reason why that is if you've got big currents and big voltages across these breakers, you've got to have them shut really fast, because otherwise you get arcing, and arcing's bad because what happens is it ionizes the atmosphere and essentially turns the atmosphere into a conductor, and then you get shorts in all sorts of places. So you have to close those switches as quick as possible, and that's why they make enormous bangs. In fact, it's usually when I show people around the inverter, it's my favourite party trick, where I turn it on when they're not looking and then make everyone jump. So there's our big transformer, and basically, these are new pieces, relatively new pieces of kit as well, because they're air filled. Now, if you probably maybe at the end of your street, you'll see like a little, often like a little wooden fenced area with danger of death, electricity inside, and you'll see lots of blue metal boxes in there. And one of them is probably an oil-filled transformer. Now they're looking into getting rid of a lot of these because the oil is a big problem. Environmentally, it's nasty stuff, and you have to deal with it. National Grid have invested a lot of money in building systems to deal with that problem. So we're all running, but the problem is we've got another problem now, because we've got our battery system, we've built it, we're ready for dealing with. We're dealing with a changing load, so our factories and our houses and EastEnders coming on, that's all coping. And then what have we done? Well, we need to do it because it's important. We've got loads of renewables, and these are intermittent too. So not only have we got a problem with the loading changing, we've got a problem with the supply changing. So we've got two things we can't predict and doing all sorts of strange things. So this is even more reason why we need storage. To give you an idea, I mean, I was quite surprised, but I looked this up the other day, actually, off a government website. In 2015 alone, renewable generation grew by 5%. That's a huge increase. So, and this week we experienced massive increase in frequency because the solar generation farms were generating up to 3 gigawatts, which is very high proportionally for the national grid. And they just had nowhere to put it. So really, kind of getting to where we are at the moment now. So we've got our battery system, we've got these renewables going on. We're going to have to deal with these renewable systems, but hopefully our battery and many other systems will have a way of dealing with it. So the current research I'm doing at the moment is a thing called enhanced frequency response, which is it's an incentive being proffered by National Grid, and you have to get to 100% of output within 1 second. Now I know we can go to 40 milliseconds, but that's including all our transmission down the internet or our telephone line or something like that. So essentially what it means is that you have a graph and you respond to this graph. So for example, if the frequency is out by 49.9, you have to put in about just over 600 kilowatts, because that's a proportion of our total generation capacity. And there's a bit of a gap in the middle because obviously frequency isn't deviating enough to be a problem. And then on this side, so this is taking away, this is adding because it's relative to the grid. But so we've been operating along this graph. So, and these are some preliminary results we had last month. So you can see this was the frequency we were measuring, and this was our response. So, for example, we got up to 50.15 there, too high. So what we're doing, whoa, let's press the button, and we're dragging out. At that point, we're really injecting power there, because we're taking power out because the frequency has got so high. So we're really hammering it because we're taking power out of the mains at that point. And one thing you'll notice is how fast things have got to move. And this is why batteries are proffered as one of the good solutions, because it's all about speed for frequency regulation. So finally, really, you've probably heard of the term smart grid, and that's what EFR is, one of the parts of this. And when they say smart, it means you've got two-way communication between users and suppliers, and you control each side accordingly. So really, it's all about balancing supply and demand. And if you've got a store there, it gives you that buffer zone. It gives you a bit of thinking time between what you can do with it. But there are so many other things that could go wrong, because we don't know if you looked at the speed of that graph, if you looked how fast those things were moving, you might wear your batteries out too quick. What battery is the best size for doing this? Is it a battery at all? And this is the sort of stuff we're looking at. We don't know. I mean, supercapacitors would be great for that, but how many would you need? Supercapacitors aren't very good at storing a lot of energy, so you need loads of them. So then maybe that's not the best thing. So really, there's loads of questions out there. And just to finally really mess everything up, is some people now are promoting going to a DC grid, which would make possibly all of this completely pointless. But that's not really the case, because even if we did, which I don't suspect we would, not in the short term at least, even though we could do that technically now, there's other problems associated with that. And also, we will still always need some kind of battery storage system, or definitely energy storage system. Without that, well, we'll always need some kind of that. So all these questions will be answered by this enormous battery system. They're not all going to be answered, but they're going to give us some pretty good insight to do with it. So, and that's where we are at the moment. And that's me. And I'm now going to attempt to minimize this and go back to not screen sharing. It's thinking. And there you go.
Okay, and thank you ever so much, Dan. Blown my mind very much so, and I hope people have realised, or begun to realise, quite the complexity that we have in the systems that we probably assume are just every day. You know, we go and turn on the kettle and we just expect it to work, don't we? And it's incredible to actually dig a little bit into these systems and see you know, the level of complexity and the amount of resources that are put into these things. Now, we are going to do some questions. I think we've got time maybe for about 10 minutes to discuss some of the key ideas and play around with them a little bit more. Unfortunately, I know that a couple of the students from Classroom have struggled to get in here. We've got 3 students from a Donato group. Unfortunately, the group from JSA have been struggling to get in. Just because of a glitch in the Hangout. But fingers crossed, the Donato students have lots of good ideas in this, and I'll also check in to see if we've got any questions coming in from the YouTube followers as well. So feel free to ask questions away. I've got some interesting ones. Megan's asked a question in the chat. Megan, would you like to mic on and ask that?
Okay. Well, why would we want to switch to DC? Because that would be a big change.
Dan, you're muted. Just to say, to stop some bounce back.
Is that better?
Yeah,
can you hear me?
perfect.
Yeah, right, sorry about that. Me and technology, eh? Well, the big thing with DC is that one of the main reasons why, so for example, there are some parts of the grid that are DC. The cross-channel link is DC. I believe there's a link down, or it's either being built or has been built, going out from Scotland to further down the west coast of the UK. And the reason for that is you reduce your capacitance in your cables, and which is an enormous saving when you start to get into big distances and big currents, or big distances and stuff. And really, that's one of the main reasons. Also, the DC to DC converters now. So essentially, what runs your laptop, you switch mode power supply. They can now make those in enormous scale. Obviously, in the kilovolts. They don't work quite the same, but essentially that's it really. If you went to DC, you'd have a lot of energy savings. And also, most of our appliances now are DC. So, for example, this laptop is DC. All your any electronic appliance is DC, from an IT point of view. So there's loads of reasons for. So if you kept in DC, you'd keep it all the same. And another reason, and AC, if you're generating in this alternating current mode, you do give off a lot of stuff called noise, for want of a better term. And mains noise is very detectable. It causes lots of trouble with transmission of radio frequencies and things like that. And all sorts of other. And I'm probably forgotten loads of other reasons why. But the key point is we couldn't do DC before on a cheap scale, and we can now. And all of a sudden, people are saying, well. I'm just thought of another one as well. We generate solar power by DC. If you, at the moment, and from the battery. So if we started putting more of these battery systems in, and more of these PV, as we've got quite a lot already, we wouldn't have to sort of get it through another inverter stage. That's an efficiency loss. It's only 2 or 3%, but on a grid scale, that's a lot of energy. So there are reasons. So that's it, really.
Fantastic. I'll just go to the floor again. Does anyone have another question they could come in with? And I've got a couple myself if they've. Okay, we'll give them a chance to chat because sometimes they do come through in the chat as well. Just to call back, we've been doing a little bit, or we discussed a little bit in class about the idea of the Internet of Things, and you kind of touched on that point a little bit with the discussion of two-way grids, kind of communicating grids. Would you like to expand a little bit on what that kind of means, but also what the benefit of it is in terms of energy generation and actually how it benefits the systems that you're developing in your work?
Well, essentially it gives you a method of prediction. So if you had each home with a smart meter, let's just say our internet was a bit less, a bit more redundancy grid and things. So the dream would be is you'd have a fantastic internet connection between any person using your electricity. Then you could much quicker work out where your demand was and even predict it where your demand was going to be. So, and then what you could do is instead of having a giant battery, perhaps, and people looking into this, a giant battery like we've got at Willenhall, you can have a smaller system in each home. And then if the communication was good enough, you could sync those batteries. But obviously it's all dependent on communication. As a silly side note actually, E.ON have looked at this and they've said they really don't want to be putting optical fibre connections into, if they put these big batteries on some of their installations. They don't want to put, they've looked into saying, I'm not sure about, and they've been asking us a lot actually about how we're getting on. Because by sheer chance, we had a logistical problem and our fibre connection has been 2 years late, and we've been relying on a little 4G dongle, believe it or not, for running the thing remotely. It's actually turned into quite a good little research thing on its own because it showed whether this is a practical way of doing it, which it would save a lot of money. Getting an optical fibre across a substation is quite an expensive process. So, and dangerous actually if you don't scan the ground right. So, and we've thrown all sorts of logistical issues with that. So we've had birds doing their mess on the antenna, which we lost the system. But believe it or not, so you could have 1.3 million pounds of battery disabled by 2 pigeons. So it's all about actually, really, it's not some. The communication is as essential as the actual mechanical stuff doing the work, really. Because without it, they won't know what to do. So but the key point is you'd have to tie everything together. And there's a lot of research, a lot of IT sort of based research going on about that.
Okay, fantastic. And a very interesting development there coming in as well. One more question kind of coming in from the floor. With these battery systems and actually the storage system, I guess one of the questions people might be asking if they're watching this, especially coming through from GCSE and A-level, we do a lot about the comparison between renewable energy resources and non-renewables, is large-scale grid storage potentially could almost, as you're doing with the frequency changes in the system, on an even bigger scale, I guess you could actually massage the amount of energy you've got to actually use renewables more. I was wondering if you have an opinion on whether 100% renewable energy is actually a pipe dream, or it actually could happen within this kind of massive use of these kinds of systems.
I think it could happen. But it will take a lot of other things. For example, there's a lot of interest in the thing called demand-side management. So you're not just talking about how you generate it or even how you store it. It's how you use it. So almost coming back to your smart grid thing, if you can either predict it or even tell people to turn stuff off when they're not using it, or even a central controller, which would scare a lot of people, but turn stuff off when it's not being used, it would make a massive deal. So I think it is possible. I mean, if you look at, here's the basic economics. If you're looking at that nuclear power station that is not even being built in the news at the moment, I believe it's going to be about £15 billion. Now, that's a lot of money for a nuclear power station, but that's how much they cost. Fair enough. But it's only tens of gigawatts power. If you got 1,000 of our systems, and I reckon you could get a discount on if you bought enough of them. So if you have 1,000 of those systems, it's only 1,000 containers, plus probably another 1,000 for the inverter systems. So you'd have 2,000 containers. I've seen a container store near Peterborough that's got more than them. So if you had 2,000 of these containers, now it would be enormously complicated. And I don't think I'd choose this method of doing it, to be honest, because the cell balancing would be a nightmare. But it would only cost you about £1 billion. That's only another billion on the end of 15. But it would give you enormous flexibility of a nuclear power station. So obviously nobody's going to commit to that. And to be honest, using this system scaled up like that probably wouldn't. There's better ways of doing it with a bigger battery. You can use a flow battery or even compressed air storage or something like that. But if you look at the sums, they're starting to make sense. And I think in maybe a generation or two, I think they definitely will make sense, because it's not about necessarily resources. There'll be some other factor that will come into play. It will be more to do with not just resources, but it will be to do with energy security, or for want of a better term, there'll be some international instability or something, and then suddenly it will become a much bigger priority to spend more money on fixing these things. And we're at a very big crossroads anyway. The national grid. Our national grid has been underfunded for a very long time, and a lot of it's in quite poor state of repair. That's for a number of reasons. That's sort of nobody's fault and everybody's fault. You could go on all day about that. But the key point is I think it's a kind of a crucial time, because if we make the right decisions now, we don't have to spend the money twice. But I do think so. I think in maybe a couple of generations' time we'll be getting there. I think we've got to sort of gamble on building stuff that's not great now, but it will get us over it. But with the wind turbines and the solar, if you look at there's I'll send you this, I'll find it again, but there's a very good website you can find which gives you live national grid statistics. And if you look at it on a day like today, you'll be staggered by how much renewable has been generated now. So it's all about storage in some way or form in an economic manner. But maybe in 2 generations' time, I reckon. That's my guess.
So what we're predicting is the next Suez crisis for this generation. And just to lead, I guess the final question there, bit of history there, if there's anyone watching, feel free to look it up. So I guess the crucial question I'd like to just have your insight on is a little bit is if someone is wanting to become the next engineer who's going to solve these problems, could you give a little bit of background just how you got into the industry and how your route into it? I think we're going to finish off after this question just because obviously we want to keep within the hour roughly, but yeah, it'd be really interesting.
I started off as an electrician. I did my A-levels, but I was actually doing my A-levels. I was quite young. I was quite small during the recession of the early 90s, and I never wanted to be unemployed. And I remember the only people who had employment, even though they weren't doing that well, were the tradesmen. So I thought, well, I'll do a trade first, because I wanted to join the army, but the army careers officer told me to get a trade first, because he was a chippy. He told me to get a trade first, and then you can think about everything else. So I did my A-levels, because they were free at that point. I mean, they're the last time they're free. And then I did an apprenticeship electrician, and I was very fortunate. I wrote a lot of letters halfway through my apprenticeship to get sponsored to go to university, and companies sponsored me to go to university, so I did an undergraduate degree at Loughborough, and then I've done a few other things, and then I did a bit of travelling, as you do, and then I decided I wanted to do a PhD, and I did my PhD about heating systems, domestic heating systems, control of them, but also at the time this battery, I was getting a bit of an interest, and there was a couple of other PhD guys doing battery stuff at the time, and I kind of drifted into it. But as long as I'd recommend engineering to anyone, particularly at the moment, because there's so much scope for it. Electrical, mechanical, civil, all of those things, there will always be scope for engineers. It's something you don't really think of as a school. It's kind of like, because you don't do A level, well, you do now. You don't. In my day, you didn't do an A level in engineering, so to speak. So it's kind of a bit abstract when you're 16, 17. You don't really kind of know what it is, unless like me and my brother did it. So. But that's how I got into it, and I really enjoy it. So yeah.
Well, fantastic. So I think we've come up to the point where we've had the hour, and I think we've had a fantastic introduction to the weird and wonderful world of electrical engineering and how it can be used to solve some of the big problems in the country, which I think are coming up. I'll just leave it for the students to say thank you for Dan Rogers giving his time. I hope they've really been inspired to kind of think a little bit more beyond the A-level and the blue sky things that we've been thinking about, but also thinking about really the applications and where the value is in a lot of these technologies as well. So thank you ever so much for joining us, Dan, and it's been an absolute pleasure to hear you talking. Now I'm going to stop the broadcast, so goodbye to anyone watching on the YouTube channel.